I'm Benjamin Cosman. This is local refinement typing. So first, if you're unfamiliar with refinement types, a refinement type has two parts. There's a base type and a predicate. So in this example, we have nat, which has the base type of int, and the predicate being non-negative. So this is the natural numbers. Here is the code for the absolute value function written in Haskell. And so it takes in an arbitrary integer and returns a natural number. And we can check this, that the code meets the specification, by creating a verification condition. So for example, this second line corresponds to the otherwise case. So when n is negative, it must be the case that 0 minus n is an acceptable nat return value. And once we have these verification conditions, we can check that they're valid using an SMT solver, which will show that the code is safe. So now that you're acquainted or reacquainted with refinement types, here's our problem. So we'd like to do type inference for refinement types. And in the presence of local variables, collections, or higher order functions, this requires us to do some type synthesis, which is hard. Let's look at examples of each of these three things. So first, local variables. So this example code here, it's just the identity function for numbers written in a strange way. So we decrement a number and then increment it again. And most of the types are easy to figure out. We have t is equal to x, so its type is just a value that is equal to x. Decrement t, we can get its type right out of the library definition. So it's a value whose value is 1 less than t. And similarly, increment y comes right out of the library definition. But we also need a type for y. And it can't depend on t, since that's a local variable that goes out of scope. So we'll need to find something else for it. The simplest, perhaps simplest type we could give it is almost nat. It's a number that's no smaller than -1. But that type doesn't appear anywhere in the code or anywhere in the library, and so we'll have to synthesize it. Here's an example with collections. So we have, again, an input x, which is a nat. We have n and p, which are both within plus or minus 1 of x. And so when we stick them together into this collection y's, then we'll need to be able to tell that y's is a list of almost nats, in order to tell that taking the last element of it and incrementing it gives us a nat to return. And finally, we have higher order functions. So fn just decrements numbers, fp just increments them. And so when we compose the two, we should get the identity again. So that has type nat to nat. In order to prove that, though, we'll need to show that fn has type nat to almost nat, and fp has type almost nat to nat. So here's some prior work which takes a crack at this problem and solves it for example 1. We can add the existential quantifiers to our refinements, and this lets us handle local variables that go out of scope. So in this example, we know the type for t and dec t already, and so the type for let t equals x in dec t is just there exists a t, which follows the previous refinements. And so now we can safely refer to t like that, as long as it's wrapped with this exists. So we can handle local variables like this, but this doesn't extend to the other examples with collections and higher order functions. So here's our solution. We have 3 steps here: assigning templates, generating constraints, and then solving. And I'll explain what each of these are using those examples. So let's go back to example 1. So we had that y that we couldn't tell what the type was before. So let's just give it a temporary type, this template k. So it represents some unknown refinement. Now we can generate constraints, just like these will be just like the verification conditions from the beginning of the talk, except there'll be k's floating around. So we have there. So when x is a nat, and t is equal to x, then we know that v being t minus 1 implies k. Whatever type y has is the same type as what t minus 1 had. And given that type k for y, we know that y plus 1 had better be a net, so we can return a net. So now that we have this constraint, the program is safe if there exists some predicate that we could replace k with that would make this formula valid. So let's solve for k. So first, we're going to only look at the first line, the one where k is on the right-hand side, and solve for k just with that line. Now, there are many solutions there, including just the trivial solution, k equals true, because once you have any left-hand side will imply true. However, we know what's coming next, which is that we're going to be using k on the left-hand side of some implications. And so we don't want to choose a trivial true. It doesn't help us when it's on the left. We want instead the strongest solution possible for k. And when we have a bunch of hypotheses that imply k, the strongest solution is essentially just the conjunction of those hypotheses. The implies turn into ands, the for alls turn into exists, and there's our solution. And this conjunction with those four conjuncts may not look very pretty, but it is equivalent to that almost nat property that we wanted. And so when we take that solution and substitute it in to the second constraint, and I'll substitute in the simplified version so that it's easier to read, then the SMT solver can tell us that this is valid, and the program type checks. Let's do it again for the second example. So here we have the types of n and p are easy to see from the library definitions of decrement and increment. X's and y's are going to get these temporary k variables, so we have kx and ky. And then we can figure out the rest of the types from there. Y is an element of y's, and incrementing y, you just get y plus 1. So those are our types with some unknowns in there. Now to generate constraints, we have, in the case where x is a nat, and the facts that we know about n and p, all of those things imply that, well, n is a valid element of x's, so a value being n must imply kx. And similarly, p is being put into y's, and so v equals p implies ky. And also x's, so all the elements of x's are getting dumped into y's. So kx implies ky. And then we have the remaining constraints of given the type ky for y plus 1 has to be a nat. So we'll solve these in the same way. On the left, I'm highlighting only the parts of the constraint that involve having a kx on the right-hand side. And so we can then solve for kx, which is just those same predicates with some exists in there. And we could just use that solution for kx, plug it in, and proceed to solve for ky. But that solution's already rather large. And if we plug it in and solve for ky, all of that stuff will end up in ky as well, and it'll be even larger. So I'll first introduce our key optimization to make this smaller so that it's more practical to work with. So you'll notice that the constraints on the left maintained the scoping structure of all the variables. And in particular, x, n, and p are all in scope everywhere where kx appears, both on the right and on the left. And so we can actually leave out those green predicates about x, n, and p from the solution for kx. We can omit them entirely. And we get this much smaller solution. And we know that when we plug in that solution, the predicates we omitted will still be there in scope. To keep the slides readable, I'll plug in a slightly smaller equivalent solution, but it would still work if we plugged in the solution, the full solution. So So there's our solution for kx, and now we solve for ky. And again, we just take just consider the constraints where ky is on the right-hand side, get a solution based on just those. So once again, the for alls become exists, the implies become the ands, so ands become ors. And just like with the previous one, I've left out the green predicate for x because it's in scope everywhere. And now we can take that solution and plug it into our final constraint, and we get that this is valid. And let's do it one more time for example 3, a lot faster. So there's our types with a bunch of k's floating around. There's our constraints. The first one comes from the input type being nat. The last one comes from the output type being nat. The middle two are from our functions fn and fp. And we can start solving for the k's one at a time. So here's the solution for ka, plug it in. The solution for kb, plug it in. Solution for kc, plug it in. And each time, just to keep this readable, I'm plugging in a simpler version of the solution, but it would still work if we plugged in the entire thing. So, and this final one is valid. So let's see what we get from this. We integrated this fusion algorithm into liquid Haskell. And so fusion takes sort of a first pass at the synthesizing types. It can handle straight line code, but whenever there's recursion, you end up with a cyclic dependency, where say the same k is on the left and right of a constraint. And so our solution doesn't work there anymore. Doesn't help if the solution for k has a k in it. So then we fall back on liquid typing. And liquid typing can handle those recursive ones. It synthesizes those types using the user-supplied building blocks we call qualifiers. So this, we have two different benchmark suites. The first one is 11,000 lines of Haskell standard libraries in which we verify all sorts of properties, including safe array accesses, termination, and so on. And the savings from Fusion are somewhat variable, but there are cases where it saves us up to half the time and up to half of the qualifiers. And then we also have a set of theorem-proving benchmarks. So recent work, which you can hear presented on Thursday if you stick around, shows that we can use refinement type checking to check theorems. So for example, this code snippet on the right is a proof written in Haskell that the maybe instance of functor satisfies the functor laws. It's a piece of the proof. And so these proofs tend to be almost entirely straight line code. And so liquid Haskell with Fusion makes quick work of them, verifying 1,000 lines in just 19 seconds with almost no qualifiers. And yet, the types involved from these intermediate terms can be complicated enough that for most of these proofs, liquid Haskell without Fusion finds it just impractical to verify them at all. Other things you'll find in the paper include why this problem is hard and why what we do is sound. And that is all I have. Any questions?